Our today's topic is Huffman algorithm. So encoding and decoding both. But before discussion of this topic, we should know that what is binary tree, what is two tree, extended binary tree. So firstly, we will define what is two tree, extended binary tree. It is also known as two tree, and some observation we will take, and after that what is the need of this algorithm, so the problem for that, and then we will discuss the algorithm and encoding and decoding part. So what is extended binary tree? Extended binary tree, which is also known as two tree, is a tree, is a binary tree which has either 0 or 2 children. We know that in binary tree we can have 0, 1 or 2 children, but in extended binary tree, and that's why it is also known as two tree, either 0 or 2 children any node can have. So nodes with two children are known as internal nodes, and the nodes with 0 children are known as external node. So to represent external node, we use circle, and to represent external node, we use square. So you can see, if it is a binary tree in figure A, which is shown, and converting this binary tree into two tree by replacing each empty subtree by a new node. So we can do this like this. You can see it is empty, so we are representing through this node, external node. Now, for Hoffman algorithm, I am taking this example. So you can see it is a extended binary tree. In this two tree, you can see that internal node 1, 2, 3, 4, 5, 6, and external node 2, 4, 6, and 7. So total there are 7 external node and 6 internal node. So you will have the relation an external node is equal to an internal node plus 1. So this is true for all two tree. This is true for all two tree. An algorithm can be represented by a two tree where the internal nodes represent tests and external node represent the action. So what will be the running time? So running time may depend on the length of the path in the tree. So that's why path becomes very important. If you find out the path length of this two tree, so we will get the length sum of internal node is equal to 9 and external node as a 21. So again we got this relation L external is equal to L internal plus 2n, and it is true for all two tree. Here this small n is number of internal node. Now suppose T is a two tree. Suppose this it is a two tree with an external node, with each external node having non-negative weight. So what will be the weighted path length? Weighted path length is equal to weight and then length. So suppose the first one is W1 weight and the length is L1 plus W2 L2 and so on. So where Wi and Li is the weight and path length of the external node. So weighted path length will become this one. So now take three example we are taking here. You can see the weighted path length of this we are getting 42. The weighted path length of this we are getting 48, and weighted path length of this we are getting 36. So see, this P1, P1 and P3 indicate complete tree need not give minimum length. P1 and P3, P1 and P3 indicate complete tree need not give minimum path length. You can see here we are getting 42 and here we are getting 36. So it is not complete tree, but we are getting minimum path length here. Similarly, P2 and P3 indicate similar tree. This and this both are similar but need not give same length. So it do not depend on whether the both tree are similar, or if it will be complete tree then it will give minimum. No. And that's why a problem arises. So what is the solution? Now, another point before discussing the Huffman algorithm, we know that we use compression techniques to compress files and messages, and each character requires approximately 1 byte or 8 bits. So, already wasting 1 bit for other purposes. Now, the question is, what is the smallest number of bits that can be used to store an arbitrary piece of text? So the very basic idea of this Hoffman encoding is find the frequency of occurrence of each character. If the character is frequently used, then allot short bit strings, and if it is rare characters, then longer bit. So the algorithm is very simple of this Hoffman algorithm. The purpose of Hoffman algorithm is find a tree with minimum weighted path length. तो मैंने अभी weighted path length की बात आपसे की. So this algorithm is used to find the minimum weighted path length. First step, we take two weight, we take two weight W1 and W2 where both are minimum weight among all the existing weights. Find a tree T dash which gives solution for n minus 1 weight. So this W1 plus W2 we are combining, and so we are getting n minus 1 weight. So find out the solution for that. And whatever the solution we will get, after that, after getting the solution, we will replace in T dash by this one. So W1 plus W2 will be replaced by this one, where it is an internal load. Left child is W1, right child is W2. So this new tree will be the desired solution. So it is a kind of recursive solution. Now, now about the Hoffman encoding, we will take this as an example. This is the tree. Suppose we take a random tree, like we have taken this one, and encode by this way: left 0, right 1, left 0, right 1, and so on. And whatever the character we have here, allot the string. Frequent character 2 bit and other 3 bit. So this is the way for encoding. Now, suppose the initial sequence with frequency we have A and F, E, C, B, D, A, and this is shown as the frequency. So what's the algorithm says? Algorithm says combining two, combine lowest two into subtree. So the minimum we have F and E, so we are combining 5 and 9, we are getting 14. After combining this will be the internal node. 14 will be at its appropriate place, so move it to correct place. Now here it will be shifted, so 12, 13, 14, and then this one. Now again combining two minimum, so this 12 and 13 both are minimum, it will be combined, it will become 25. Again we will shift here because this will be the sequence, so move subtree to correct place. Now again uh, moving here, so move the new tree to the correct place here. Now the lowest two are this 14 and D. So 14 and 16 we will combine, we will get 30. So it will come here. Next one. So we are moving here. Now the minimum will be 25 and 30. Again we will combine and then it will be moved to correct place. And after this 45 left and 55 right, we will get this Huffman tree. We say it is Huffman tree. And not now for encoding purpose we left age we assign 0 and right assign 1. So the coding of A will become, we start from root, move here, so root, so here we are getting 0. For C, 1, 0, 0. For B, 1, 0, 1. For F, 1, 1, 0, 0. E, 1, 1, 0, 1. And for D, 1, 1, and 1. So in this way we can encode. Now the decoding part. Suppose we get this message, so how we will decode it? So start at the root and go right. Why? Because we are getting 1. So 1, so we'll start from root and we will go right. Then again, because 0, then we will move left, go left. Chuki, this one is the root, so we get T. So we will decode it as a T. So output is T. Then again we will go to the root. Again we go to the root. We are getting 0. So 0, so left, go left. Then after that again we get 0. So again left. And now it is leaf. So output we are getting E. So output is E. Now again if we start from the root, we are getting 1, so right. Again getting 1, so again right. And again getting 0, so left side, go left, and you are getting output, this is N. So this is N. So in this way we can decode. So we discussed today that how we can use the Huffman algorithm, in what the circumstances the Huffman coding is desired, what are the benefits, and encoding and decoding part. So enough for today. Thank you.